Electrostatics is the science of charges at rest, the invisible forces that make your hair stand on end and cause lightning to strike. In this video, we'll uncover how charges interact, why opposites attract, and how electric fields shape the world around us. From shocking experiments to the fundamentals of force, get ready to see electricity in a whole new light. Briefly, before we get started, I just want to say that electricity is probably the first time in physics where we really are not going to have a realistic experience that we can see or feel with electricity. You might feel a slight attraction or repulsion. You may have felt a static shock. You may have seen lightning strike, but most of the physics around electricity is going to be very difficult to visualize. So I encourage you to keep your imagination strong in this one and really spend some time thinking outside of the box. Good luck. Electricity was first discovered by the ancient Greeks, who noticed that when polishing amber stones with a piece of silk, that amber then attracted small bits of straw. Really what's going on here is that both objects are initially neutrally charged. They have the same amount of positive and negative charges within them. The silk has a little bit of positive and negatives, and the amber has a little bit of positive and negative. And when we rub those two pieces together, the charges within those materials are exchanged. The material that is more electronegative, in this case the amber, will strip electrons away from the other material that's more electropositive, the silk. After separating these two objects, we'll see that there's a collection of charge on each of the objects, and this charge seems to be different for both of those two objects. The amber seems to interact with other charged objects differently than how the silk appears to interact with other charged objects. This gives us the idea that there are really two types of charges. There is negative charges and positive charges. And we notice that every time a negative charge is created, it is always coupled with a positive charge somewhere else. And we call this idea charge conservation. We now see a unique application of the electric charge, which we use the letter Q for in physics class. Electric charge is ultimately based on the electrons inside of materials. Those are the things that carry electric charge. And electric charge is a fundamental property of matter. This is just as fundamental to our existence as mass itself. There are only a few fundamental properties of matter, and charge is one of them. It's measured in the SI units of coulombs, which has the letter C for that unit. Electrons are the charged particles within an atom that are exchanged to impart charge onto some object. One electron has the charge value of negative 1.6 times 10 to the negative 19 coulombs. That's a very small amount of charge for each individual electron. And this value is known as the elementary charge value. So in general, the absolute value of the charge of an electron or a proton is 1.6 times 10 to the negative 19 coulombs. And this is known as the elementary charge value because this is the smallest amount of charge that could ever be exchanged in any type of process. You can never exchange a fraction of an electron's charge. Every time an object rubs together, it will always at least exchange one electron, and therefore it will always at least have a charge imbalance of that elementary charge value. As stated previously, there are two types of charges, positive and negatives. This is a fundamental property of charge, and it's different than mass and many of the other fundamental properties of matter because there's really two types, positive and negative. And when we bring two charged objects near each other, we see that like charges will repel from each other, and we call that electrostatic repulsion, and unlike charges, opposite charges will attract to each other, and we call that electrostatic attraction. We can see this in the experiment at the bottom, where if we have a positively charged glass rod, it will be attracted to a negatively charged piece of silk or cloth. In this way, the opposites attract toward each other, and they will feel a force toward each other. On the other hand, if we have two positively charged glass rods, they will feel a force pushing each other away. And that's the same if we have two negatively charged pieces of cloth. Again, this brings up the idea of charge conservation, which says that the total amount of charge in an object or a system will always remain constant. In other words, for every time that there is a negative charge created, a positive charge is created somewhere else. And the total amount of charge on an object can be calculated by taking the number of extra electrons or the deficiency of electrons and multiplying by that elementary charge value. That will give you your total charge on some object. If these charged objects are attracting or repelling each other, that means that they are pushing or pulling on each other. That means that these charged objects are exerting a force on each other. And this is a new special kind of force that we call the electric force. This is the attraction and repulsion of two charged objects. Of course, the electric force still has the SI units of newtons, and we can calculate the electrostatic force through Coulomb's law, where the force of electricity is equal to a constant, Kc, times the charge of the first object, times the charge of the second object, divided by the distance that separates those two objects. This distance will be measured in meters, of course, and the charges would be measured in coulombs. This Kc value is Coulomb's constant, which is 9 times 10 to the 9 Newton times meter squared per Coulomb squared. In this equation, of course, force is a vector. It has a direction. It can either point left, right, up, or down. But in this equation, you'll notice we're only calculating the absolute value, the magnitude of that force. In Coulomb's law, you first want to calculate the magnitude of the force, and then ask yourself, after you calculate that, what way should this force point? You want to determine the direction after you've calculated the numerical magnitude of that force. So if you look up at this example up at the top, we see that there are two negatively charged objects. I could calculate the force that they will exert on each other by using Coulomb's law, Q over R squared. But each of these charged particles will be feeling a force in a different direction. The charge on the left will feel a force to the left because it's being repelled, and the charge on the right will feel a force to the right because it's being repelled. And in this way, you always have to ask yourself, what way would the electric force point? Of course, force is also a vector, which means that if you have multiple forces acting on one system, you will need to add those forces together using vector addition, considering the direction of each of those forces and adding or subtracting them in their respective components if necessary. For example, if we had a 3-charge system with Q1, Q2, and Q3, we could calculate the force that was felt by Q2 first by figuring out the force of charge 3 on particle 2, that would be upward. And then we could calculate the force of particle 1 on particle 2, that would be to the right. And if we wanted to figure out the total electric force, we would have to use vector addition to determine that force that is felt by charge 2. Just to follow up on that a little bit more, of course, Coulomb's law is technically a little bit more complicated than was shown in the past slide, but I recommend you follow the steps in the previous slide to keep it simple. In truth, Coulomb's law could be calculated directly as a vector force, as long as we consider the unit vector that operates on that force. This unit vector, r hat, points from the agent to the object of interest, or the system that's feeling that force. And this is basically a way of determining the direction of the force. The unit vector just contains information about the direction, but does not have any magnitude. And furthermore, the Coulomb's constant is actually based on more physical variables in the universe. Technically, it is based on 1 over 4 pi epsilon naught, where epsilon naught is known as the permittivity of free space. It's a constant in our universe. But ultimately, this whole form of Coulomb's law is probably a little bit outside of the scope of what's expected in your current course. But if you like thinking about it from a unit vector perspective, you can always do that. Here we see an example of Coulomb's law at work, where these two agents are holding on to two charged balloons. The first charged balloon has a charge of -10 microcoulombs, and that's more like a realistic value that we could expect for the charge. And charge 2 has +10 microcoulombs. In this way, we see that they both exert a force on each other. These forces are equal and opposite according to Newton's third law. The force of charge 1 on charge 2 can be calculated, or the force of charge 2 on charge 1 can be calculated. And this force would get stronger the closer together that we bring these objects. As our R number decreases in the denominator, the force increases for these two charged objects. So now, in addition to everything that you've already learned up to this point about forces, we add in one more force. And just as a review for those of you rejoining Physics 2, here's the conventions for most of the forces that you've dealt with up to this point. The applied force, the gravitational force or the weight, the normal force or the surface perpendicular force, the tension force, the spring force or the elastic force, the friction force, the buoyant force, and of course now the electric force, which operates between two charged objects. Do not forget about all of the standard techniques that we've used to analyze forces in the past, especially the free body diagram, which involves choosing a system and writing out all of the external forces that act on that system. For this free body diagram, we approximate our system as a single point in space with its center of mass centered at that point, and any external forces will be drawn as arrows extending from that dot in their respective direction, with the size of the arrow being relative to the magnitude of the force. For example, if we have two forces that are pushing in different directions on this ice skater, we could figure out the total force by doing the vector addition of the individual forces. There are two main types of materials that can hold on to charge. There are two different types of electrical materials. The first is called a conductor, which allows for electric charge to freely move within that object. This is due to the presence of free valence electrons in the conduction band of the electronic structure in the material. And we would say that conductors have very low resistance. Some examples of this would be like water, gold, copper, other metals, and things like that. On the other hand, insulators are the opposite of conductors. They do not allow for charge to move freely within those materials, and that's because the valence electrons within the material are tightly bound to the specific atoms. And we would say insulators have a very high resistance. Some examples of this might be like wood or rubber. Those are two examples of insulators which will hold on to charge but will not allow for the charge to move freely within the material. For example, if we take a look at these objects in this simulation, we have a balloon here, which is initially neutrally charged, our wool sweater, which is also initially neutrally charged, and a wall that is neutrally charged. This wall acts as an insulator and will hold on to those electrons and keep them bound closely to their initial residence site. So let's see what happens when we take this balloon and rub it up against the wall. When we rub these two insulators against the wall, they both hold on to their individual electrons and don't exchange them freely. But because the balloon is much more electronegative than this wool, we can rub the sweater with the balloon, stripping the negative charges from that sweater. And now our balloon has a bunch of negative charges collected on it. And that means that if I let this balloon go, it will feel an attractive force toward a positive object. Now, if I was to take this charged balloon and put it near an insulator, you will see that the electrostatic repulsion causes for the electrons within the insulator to be pushed away slightly. It's like they're polarized a little bit, but because both these materials are insulators, the electrons stay close to their initial residence site where they started. We can use charge distribution diagrams to represent how the charge is distributed throughout a material. We draw positive charges as pluses and negative charges as minus in these diagrams. And for an insulator, the positive and negative charges will stay bound close to each other in a little pocket that is near where they started. This is because insulators don't allow for charges to move freely within the material. And for conductors, positive and negative charges can move all the way to one end or toward the surface that is closest based on attraction or repulsion as needed. So for example, if we take a look at this conducting rod and we bring it near an insulator, we will see that that positively charged rod causes for all of the negative charges within the insulator to lean a little bit to the left and the positive charges to lean away to the right. And we would say that this insulator now is slightly polarized, as if it's got a leaning or an uneven distribution of charges within the material, but it's not like it has an overall negative or positive charge. It's still electrically neutral, even though the negative and positives are leaning one way or the other. If we bring a negative charge rod next to that insulator, we would see the opposite trend for the polarization of charges within that material. And if we bring a negative rod near a conductor, we would see that the charges within the conductor would not be bound to their local site where they started, but instead all of the positives will move as far as they can toward that charged rod to be attracted to the negative, and all the negative charges within the conductor will move as far away as they can based on electrostatic repulsion. This is the difference between insulators and conductors. Conductors let charges move freely throughout the material, and insulators keep the charges bound close to where they started. So to actually impart charge onto an object, there are several methods for charging an object. Two of those methods happen through direct contact between the objects. First, we have the triboelectric effect, which involves rubbing two materials together such that they exchange electrons based on their electronegativity. The more electronegative substance would strip negative charges away from the other substance that is more electropositive. One example of this is like running a comb through your hair. Your hair has a different electronegativity than the comb, and that causes for a difference in charge to be collected on both objects depending on their electronegativity. The second method of charging an object is by conduction, which means that we exchange electrons between two conducting objects through direct contact. When conductors are in contact with each other, their charges can move freely within that material. So if they actually are touching, the charges will distribute themselves as much as they possibly can according to electrostatic repulsion and attraction. If we bring this positively charged rod near a neutral metal sphere, first off, those charges would end up leaning within the sphere closer to the rod based on attraction and repulsion like we saw in the last slide. But when they actually come in contact with each other, the charges will distribute across these conductors as much as they can to minimize that electrostatic repulsion. So we got a lot of positive charges on the rod to the left, and we're neutral in the ball on the right. And so those charges are going to distribute themselves across both conductors as much as they can, meaning that some of the positive charges will leave the rod and hop onto that metal sphere, and then those positive charges will spread out onto the surface of the sphere as much as possible and spread out as much as possible on the surface of the rod as well. It is also possible to charge an object without direct contact. This process is a little tricky, but it's called charging by induction. So let's go ahead and take a look at it one step at a time. First, we can have two neutral conductors in contact with each other. They have positive and negative charges in them, but overall they are neutral. Then if we bring a positively charged rod or object near these neutral spheres, all of the positives and negatives that were within those materials will lean. And since these two conductors are in contact with each other, all of the positive charges are free to move as far away from the positively charged rod as possible, and all the negative charges within both spheres are free to get as close as possible as they can to that positively charged rod. This is an example of polarization, which is a leaning of electric charge without an overall positive or negative charge on the object. The object is electrically neutral, even though one side of the object has a different charge than the other side of the object. Now, if we take these two spheres, which has negative charges collected on the left sphere and positive charges collected on the right sphere, if we physically separate those two spheres, now those conductors are no longer in contact with each other. The negative charges are stuck on this left plate, and the positive charges are stuck on this right sphere. And then if we remove the rod that initially caused that polarization, now the conductors are not in contact with each other, and all the negative charges are stuck on the left sphere while all the positive charges are stuck on the right sphere. And now we have officially charged these two objects by induction. We never actually touched them with a charged object to cause for electrons to flood into them or flood out of those conductors, but instead, By utilizing polarization and then physically separating the objects, we were able to impart either a negative or positive overall charge. Here are a few examples of some interesting uses of electricity and charge distribution diagrams. First off, an electroscope is a device used to measure the charge of some object. And the way that this works is we basically would bring our charged object near this electroscope device, which has a conductor connected to two conducting flaps within the material. And when we bring that object in contact with those conductors, it is able to impart its charge onto those conductors. And if it was positive, that those positive charges would flood into this electroscope, causing for the little flaps at the bottom to be positively charged, and those flaps would then be repelled from each other as they are positively charged. And the greater that those flaps repel from each other can be used to measure a greater amount of charge. A Van de Graaff generator is a device used to create large amounts of electric charge for experiments. And the way that this basically works is it has a belt inside of it that starts running in a circular path. And as that belt rotates, it rubs up against a metal rake here at point B. And the rake rubs up against that belt, creating static electricity, exchanging electrons between the belt and the metal conductor, collecting large amounts of charge on a conducting sphere attached to the generator. In this way, we can use this generator for experiments where if we touch the conducting sphere that has a lot of positive charges on it, the positive charges would flood into our body and spread out as much as they possibly could, even into the tips of our hairs. And now our hairs are all positively charged, so they repel from each other. This is one of the many interesting experiments that can be done with a Van de Graaff generator. We now introduce the idea of a field, which is a very important idea in physics class. A field is a way of representing the forces that would be felt by an object that enters that field. It's like a force field that acts on other objects that are present in that field. Let's start with an example of a field that you may have heard of and have definitely experienced in your daily life. That would be the gravitational field. Everywhere around Earth, we are existing in a gravitational field that exerts a force on us based on our mass. The units for the gravitational field is newtons per kilogram. This says how much force would be felt based on how much mass we have. And subtly, if you do enough back calculating and dimensional analysis, you would realize that g, the acceleration due to gravity, which is 9.8 meters per second squared, is actually a measure of the gravitational field of Earth near its surface, 9.8 newtons per kilogram. These are talking about the same thing. And so this gravitational field is a vector. It points toward the center of mass. If I'm on Earth's surface, the gravitational field points down at every point along that surface. So if I were to jump up in the air, I would feel a force in the same direction as the gravitational field. But it's important to note that this gravitational field extends infinitely throughout space. Even as I get farther and farther away from Earth, the gravitational field still exists, but it gets weaker and weaker the farther away that we are from the source of that gravitational field. In a similar type of sense, a charged object creates an electric field infinitely throughout space around it. The electric field would dictate the force that was felt by any charged object that was present in that electric field. So the electric field tells you the force that would be felt by another charge present in that electric field. And charged objects generate an electric field infinitely around them throughout space. This electric field has units of newtons per coulomb. This is the amount of force that would be felt per unit charge in the electric field. And we want to visualize this electric field as like a cloud that extends outward from the charged object that's generating the source. So this would be like our electric field. It's sort of difficult to represent, but you can either think about it as a cloud that is stronger in the center and weaker as we get farther away, or we'll show you some other ways of representing them with vector arrows in a bit. But you want to visualize this electric field as if it extends outward from the source that generates that electric field infinitely throughout space. And so what that means is any other charged object that was brought near that electric field would feel a force according to the electric field. A positive charge would be forced in the direction of the electric field. So if this electric field points to the right and a positive charge is located at a point where the electric field points to the right, it would feel a force to the right. Just to get some of the naming conventions out of the way, sometimes capital Q will be used to represent the source charge. This is the point charge that generates the electric field, whereas lowercase q is often referred to as a test charge. This is the charge that feels a force from the electric field generated by the source. But this is just a naming convention to help you keep track of which variable is which. Often in the textbook, and many instructors will sort of go back and forth on if they label it as a capital Q or a lowercase q, or maybe Q1 or Q2. So just keep in mind that capital Q or lowercase q could both represent a charge in coulombs. The electric field ultimately represents the force that would be felt by some test charge present in the field. So electric field is the force divided by the charge. It's measured in newtons per coulomb. And we have an equation for the electric force. That electric force was KQQ over R squared. So if I divide out my test charge, I have a way of calculating the electric field that was generated by some point charge. And of course, the electric field is a vector. It has direction, but often, just like with the electric force, we will just calculate the magnitude of the electric field using K times the absolute value of the source charge divided by R squared. And then we'll ask ourselves afterward, what way should the electric field point at some position in space? The direction of the electric field generated by a source charge depends on the sign of that source charge. A positive charge would create an electric field that points away from the positive charge, and a negative charge would create an electric field that points inward toward the negative source charge. So down here, you'll see our electric field lines are represented with these blue lines. It's a vector that points outward from the positive charge at every point in space around that source. Contrastingly, the negative charge has an electric field that points inward everywhere throughout space. And when we're representing these electric fields, we often use these continuous electric field lines, these arrows that point outward from a positive charge or inward toward a negative charge. When we're drawing these electric field lines, we can get a little bit more information other than just the sign of these charges. The strength of the electric field, its magnitude, depends on the number of lines within a certain region that we're looking at. So for part C, this diagram in C, you would see it's got more electric field lines entering into that negative charge, and that implies that the negative charge in diagram C is a greater amount of negative charge than the negative charge in diagram B. The electric field can be a very useful quantity for calculating electric forces, because ultimately the electric field will dictate the force felt by any test charge. So we have a much simpler equation that involves the electric force being related to the electric field that a test charge is in. And sometimes this equation will be a great shortcut to calculate the force felt by a test charge in an electric field. It's important to note that this entire unit on electrostatics assumes that all charges act as point charges, which means that their charge is all concentrated into an infinitely small point, much like we often would have approximated the mass of an extended body as just its mass being located at a center of mass, one individual point in the center of that object. When we're thinking about this force and electric field, do not forget to consider the direction of these forces. Right now, with the way that this is written, the force will only calculate the magnitude, and you need to think about what way the force would point depending on the sign of the test charge and the sign of the electric field at that point in space. In this way, a positive test charge always feels a force that is in the same direction as the electric field. And a negative charge, a negative test charge, would always feel a force opposite the direction of the electric field. To cover a few more ideas about the electric field, this electric field vector will always point tangent to the electric field lines. So if the electric field lines are curved, which we haven't really seen much yet, the electric field at some point along those lines would always point tangent to those electric field lines. So at that point in space, the electric field points in that direction, but at a different point in space, the electric field might point in a different direction that is tangent to the electric field lines. These electric field lines will always begin at the source point and extend outward toward infinity, and the electric field lines will never cross each other. They will never make a closed loop in these diagrams. And again, the strength of the electric field is proportional to how closely packed together the electric field lines are in our diagram. As we see here, the more electric field lines that enter or leave a charge is indicative of the magnitude of the charge at that source. So for conductors, the charges within a conductor will always distribute themselves as much as they can based on electrostatic repulsion. That means if I have a negatively charged conductor here, all of those negative charges will reside on the surface of the conductor, and within the center of the conductor, the electric field will actually be zero. The competing electric field lines within the material would have electric field lines going inward toward the surface of that conductor, and that means that those two electric field lines pulling right and left will oppose each other as vectors do, leading to a total electric field of zero within the conductor. When we're talking about the strength of an electric field, we say that the closeness of the electric field lines tells you how strong an electric field is. So if our electric field lines are all evenly spaced, as you see in this region over here, we would say that that electric field is uniform throughout space. It's the same strength no matter where I go. If I'm up here or down here, the electric field lines are always packed together the same amount. On the other hand, if I have electric field lines that are not packed together with the same density or spacing, we would say that that's a non-uniform electric field. So over here on the left in this diagram, since those electric field lines are at varying distances apart throughout space, we would say that the electric field was non-uniform. The electric field is weaker over here at A, where the field lines are more spread apart, and stronger over here at C, when the field lines are closer together. But on the right side at point E, we notice that the electric field is uniform in that region of space because the electric field lines are evenly spaced from each other. So we've established that the electric field will point outward from a positive charge and inward toward a negative charge. Sometimes you'll see the electric field drawn as a map of vector arrows throughout space. This is a much more complicated and precise mapping of the electric field at every point in space, with the size of these arrows representing the electric field at that point. Usually we will avoid drawing these vector maps, and instead we'll just think about continuous electric field lines and think about how the closeness of those field lines represents the electric field strength. But either way of mapping the electric field could be presented to you. We can calculate the electric field from some source charge with KQ over R squared and think about the direction from there about where it would point at some region in space. Remember that the electric field is a vector, and that means that if I have two sources that are generating an electric field, to figure out the total electric field at some point in space, I will need to use vector addition to add together the two electric fields from each source. For example, if I have source A over here generating an electric field, because it's positive, its electric field would be to the right at this point in space. And if I have object B as my source generating an electric field from a positive charge, it would point downward at that point in space. And so I have two different electric fields operating at this position in space. They have different directions, and so I need to use vector addition to determine the total electric field at that point in space by adding together the electric field contributions from each source. Just as a bit of a review, do not forget about your rules for vector mathematics. This includes thinking about the angle that vectors point at with respect to each other and extracting the x and y components of the vector quantity by using trigonometry. You can use this trigonometry to calculate different components of some vector, whether it's the electric force or the electric field, and you can use the Pythagorean theorem to determine the overall magnitude of a vector, and you can use trigonometry to determine the direction that that vector points based on its vector components. If we have multiple point charges, they will each generate their own electric field. And so the electric field from two different sources will add together at every point in space around those charged objects. For example, between two charges that are the same charge, like you see here, if we have two negative charges, the electric field lines would point inward at every point in space for both of those sources. And that means that the electric field from the charge on the right between the charges would pull to the right, and the electric field from the charge on the left between the two charges would pull to the left. And these two electric field vectors would be opposing each other, leading to an overall electric field of 0 between the two materials at their center. In a similar sense, we could map the electric field from two oppositely charged source point charges. In this case, we would draw out the electric field from the positive charge and the negative charge separately. That's what you see with the blue and red field lines shown. And when we add them together using vector addition, you get a total overall map of the electric field that looks like the black lines shown in this diagram. If you want to see a still image of two oppositely charged particles, the electric field we would see points outward from the positive charge and inward to the negative charge. And that means that the electric field would be maximized. It would be as strong as it possibly could be in the center here. So there would be a maximum electric field pointing to the right between these two charged particles. The simplest way of generating a uniform electric field is by using two conductors that are parallel to each other with opposite charges. If I have one plate with a bunch of positive charges distributed all throughout it on top, and one plate with a bunch of negative charges distributed throughout it all on bottom, the electric field lines would point out from the positive charge and inward to the negative charge, and everywhere between these plates, the electric field would be uniform. The field lines are evenly spread out, and so the strength is equal everywhere throughout this parallel plate system. Whether or not I'm closer to the positive or closer to the negative or farther to the left or farther to the right, my electric field will always be constant. We can calculate this electric field by first considering the surface charge density of each plate. We use sigma to denote this surface charge density. This is the amount of coulombs distributed over an area of a conductor, so it has units of coulombs per meter squared. And if we know the surface charge density, we can calculate the electric field for two parallel plates. The electric field between the plates would be the surface charge density divided by epsilon naught, where epsilon naught is the permittivity of free space. It's a constant for our universe. It's got this number right here, 8.85 times 10 to the negative 12, with some complicated units that can be mixed and matched depending on the problem. But ultimately, we can determine this electric field between two plates using the equation at the bottom here. This parallel plate conductor system is very similar to a cell membrane that has a phospholipid bilayer, where there are charges collected outside of a cell. Maybe these are positive charges outside of the cell with different ions floating around in solution. And inside of the cell, we might have negative charges. And so we have two charges that are separated by some parallel system, and that would establish an electric field within the lipid bilayer of a cell membrane. An electric dipole is two equal and opposite charges separated by a small distance. For example, if we had a negative charge and a positive charge bonded together, they would have some separation distance d, and we could say that one end of that dipole has a charge of negative q and one end of that dipole has a charge of positive Q, those charges are equal and opposite. And we would say in these materials that there is a partial charge, a leaning of the charge across the molecule, where positives are sort of localized to one end of the molecule and negatives are located on the other side of that dipole molecule. We can quantify the degree of polarity in an electric dipole by using its electric dipole moment P, which is a vector that points from the negative charge in a dipole to the positive charge. The dipole moment is calculated by taking the charge times the distance that separates those two objects. And the SI unit for this electric dipole moment would end up being coulombs times meters, charge times distance. Many molecules in biology and chemistry have an electric dipole moment. They have some polarity. For example, a water molecule has polarity because it is H2O. The H atoms, the hydrogen atoms, are mostly positively charged. They have an electropositivity compared to oxygen. So there would be a partial charge leaning with positives toward the bottom and negatives toward the top of this molecule. The oxygen is more electronegative, so it sort of causes the electrons to lean toward the oxygen within that molecule. And we would call this an electric dipole. And we could show its electric dipole moment as basically being one molecule with negatives on one side and positives on the other. And we would say that the dipole moment P points from the negative charge to the positive charge. An electric dipole has a negative charge and a positive charge. So those charges can act as a source of an electric field. The easiest way to calculate the electric field of a dipole is to think about what its electric field would be along the axis of the dipole. This is just one representation of the electric field that we could get at a region of space around a dipole. And on the axis of the dipole, we can calculate the electric field strength by taking 2 times Coulomb's constant times the electric dipole moment divided by the distance to that point in space cubed. R is the distance measured from the center of a dipole to some point in space. So you'll see this blue arrow represents the distance from the center of the dipole to some point of interest, P, and the electric field from that dipole would point to the right in this case. That's because really we have a positive charge on the right side of this dipole. It's sending an electric field outward in every direction, and it's a little bit closer to that point P in space. So that electric field from the positive charge would be a little bit bigger, and it would point to the right. On the other hand, we have a negative charge as well that's a little farther away from that point P in space. So it creates an electric field that pulls inward, but it's a little bit farther away than the positive charge was. So the electric field from the negative end of the dipole points to the left, but it's a little bit smaller. In general, the addition of this electric field from the positive end and the electric field from the negative end gives a total electric field at that point in space that we calculate as this equation in the box. Owing to the electric field created by a dipole, other dipoles in solution with that dipole will feel an electric force due to the electric field generated by each individual dipole. And that means that we can have dipole-dipole interactions that arise for two different polar molecules that are present in solution with each other. If we have, for example, HCl, where there's a partial positive charge on the hydrogen and a partial negative charge on the chlorine atom within each molecule, we would see that these dipoles would end up sort of aligning due to the electric field of each other in solution. Ultimately, you don't need to worry too much about the mathematics of a dipole-dipole interaction, but we can calculate the forces that are felt in a dipole-dipole interaction, and these are usually weaker forces than what you would see for ion-ion interactions or ion-dipole interactions. This is very similar to hydrogen bonding, which is essentially a dipole-dipole interaction that is very strong due to the difference in electronegativity between hydrogen and some electronegative element like nitrogen, oxygen, or fluorine. In this case, for something like water, we would have a strong degree of hydrogen bonding, which means that there would be interactions that keep water held together. It wants to feel an interactive force between other molecules within the water solution, and we call that hydrogen bonding. An electric dipole will feel a torque when it is present in an electric field based on its alignment to that field. Recall that a torque is usually a force vector crossed with a distance vector. In other words, we basically end up using torque is equal to force crossed with distance, which equals FD sine theta when we multiply through, with the force and the distance being magnitudes in that end representation. This means that torque is measured with the SI unit of Newton times meters, which is actually also a joule. And for an electric dipole present in an electric field, it will try to align such that its dipole moment points in the same direction as the electric field. So the electric dipole moment points from the negative end of the dipole to the positive end. And that means that the positive end will try to go with the electric field, and the negative end will try to go against the electric field. It'll try to be in the opposite direction that the electric field points, just as any charged particle would feel. This means that if we take the electric dipole moment times the strength of the electric field times sine of the angle between those two vectors, we could figure out the torque that was felt based on this dipole in an electric field. Remember that torque can either be counterclockwise, which we call the positive direction, or clockwise, which we call the negative direction of rotation. And theta here is the angle between the dipole moment and the electric field. So there's our theta. If the dipole moment points up and to the right a little bit and the field points to the right, the angle between those two vectors would be theta. This means that a minimum torque would be generated when the electric field is perfectly aligned with the dipole moment. If theta equals 0, we would have a minimum torque of 0. The object wouldn't want to rotate at all. And if we have a dipole moment that is anti-aligned as much as it possibly could be with an electric field, if the dipole is at a 90-degree angle with the electric field, it will feel the strongest torque that it possibly could to try to rotate it back into alignment. And this 90-degree angle would maximize the equation for the torque on an electric dipole. So that'll cover everything for our unit on electrostatics. This is just the beginning, and I recognize that many of these equations are quite difficult to wrap your head around the first time through. So please do take your time with it. Consider looking up the external resources that are shared at the end of this YouTube video, and also make sure to ask any questions of your instructional team to clear things up. Thanks for paying attention. I'll see you in the next one.